5 minutes of getting some teriyaki chicken, guys. It was pretty legit. I talked to the guy on this.
Kevin,
Okay, I'd like to start. Good morning, everyone. You notice we have a film crew here today. What we're going to do today is electricity. So you guys are going to learn all the basic circuits, all the basic stuff about electricity that electricians know. And electricity is a trade. So it's kind of like carpentry or plumbing or fixing cars. It's something that is a hands-on kind of activity that you can learn. And it's a chance, I think, it's certainly a lot of fun too, but it's something where a kid can learn something hands-on. And what I did when I was a kid is I learned electricity and then electronics as a kid. I went 2 years to college, and then I had a very nice job after that, and then I went to night school for years and years, and then eventually became an engineer. So electricity is that kind of thing. You can kind of learn a lot of it in a hands-on kind of fun way, which is what we're going to do today. So today we're going to talk about electricity. I'm going to show a few slides here showing the basics of electricity. Then I'm going to have you guys come up and we're going to do a water demonstration, because most people who are engineers, most people who are into electricity and electronics, we learned thinking about it like water, okay? So water is a good way to learn electricity, to think about electricity like water. And after we do our little water demonstration, you guys will go back to your desks, and then you'll start wiring your circuits. And then after that, once you guys have wired up a bunch of your circuits and you've gone through your worksheet, you're going to be rewarded because we're going to give you some little toys to play with, some very loud, noisy horns that we have here for you, for your entertainment. They're very good for annoying teachers. And you're going to be rewarded by being able to play with these. And then we will end the class by making some nice, juicy sparks. Okay? So this is all this kind of stuff that we're going to do today. I also want to point out the most important thing to say today is we're going to be using batteries today. So we're going to be using both these little flashlight batteries, and we're going to be using the batteries here with springs on them. And if you can see, I don't know if you can see from back there, but these larger batteries, these are really made just using 4 little batteries inside. Can you guys see that? Yeah. So to make one of these big batteries, it's actually good engineering. What they do is they simply drop 4 small batteries inside, put the top down, and then inside there are connections, there are wires in the top that connect these batteries up so they're connected in series, we say. And that way we make a more powerful battery. We make a 6-volt battery. But the very important thing is today we're going to be using batteries only today. Batteries are always safe. But please do not go home and fool around with the plug in the wall, all right? Because that can kill you, right? Everybody should realize that. The plug in the wall is 120 volts. It's more than 100 batteries. That's the equivalent, okay? And it can kill you. But as far as this stuff, if you like this kind of stuff, you know, this is all basically Radio Shack stuff. You can go down and just buy this stuff and do it at home and have fun, all right? But don't play around with the plug in the wall, okay? So let's do our prize time and do that, and then we'll start our lesson today. Now, again, please, let's just have this for kids who have not won a prize yet, please, so that it's fair. We give everybody a chance, okay? So for our prize time question, who could tell me what a wave is? Remember we did waves last time? So all kinds of waves, every kind of wave, all kinds of waves. Is there anyone who's not won a prize who can tell me the answer to that? What is a wave? No, hold on. Does anybody know? All right, let him if he knows. Go ahead. If nobody else knows.
A wave is like electricity moving.
It's something moving.
Energy.
Ah, good man. Good for you. He's going to get it. Nobody. Okay. I just want to make sure that if we had people who had not won a prize, they had a chance. So remember that a wave is energy that's moving through something. Okay, remember that? We did that when we did waves. Okay? All right, so let's start out. And it's important, I want to get the talking done, the lecture part done, so you can do the fun hands-on part, okay? So now, we're going to be talking about the atom in just a second, and things called electrons, which are in atoms. But the idea of all of this stuff, electricity, is we have batteries. One side of the battery has a little bump on it, the other side's flat. The side with a bump is the plus, the other side's minus. So one side connects to stuff inside that has extra electrons in it, compounds inside. They have extra electrons. The other side connects to stuff inside that soaks up electrons. So in all electric circuits, you might have a wire connected to it, and the extra electrons come out of one side of the battery, flow through the wire, go through stuff, come back, and then get soaked up. So in all circuits, electrons come out, go through stuff, come back, and get soaked up. Always like that in a loop. Okay? And we're going to talk about that right now using just a few slides, okay? Okay, now here is a diagram of the atom. And you guys will have the atom later this year in school. So the idea is an atom is kind of like a miniature little tiny solar system. And it's a good way to think about it anyway. And the idea is here in the middle, we have a bunch of stuff in the nucleus. But what's important for us today are these things here in orbit around the center. So they're not connected, they're in orbit, they're going around the center, and these little things are called electrons. So these are all inside atoms, which are very, very tiny things. You can't see atoms, even in a microscope you can't see them. But because these little tiny electrons are not connected to anything, they're just in orbit, we can run them through wires and get them to do stuff for us, because they're not connected. And if you think about the word electron, that's kind of like electricity, isn't it? Or like electronics. That's where the words come from the word electron. Now, in every electric circuit, no matter how complicated, no matter how simple, but in every circuit, we have these three very important things. In every circuit. One of these things is called the voltage, like battery voltage. Another one is called current. Usually we say current flow, or electron current flow. And the third thing is something we call resistance. Resistance. So the voltage, the battery voltage, that's really how much energy the battery has. It's how many extra electrons the battery has. How much can push those electrons through the circuit. And the current flow, if you think about water, you know, like water flowing in a pipe, water flowing in a river, it's the flow of electrons. That's what the current is. The current is the flow of electrons through a wire. Okay? And resistance, the third thing, is also very important. Resistance is, how big is the wire? Is it a big fat wire or a little tiny skinny wire? That's what we call resistance. Now I'm going to show you with water in just a minute. I think it's a little easier to understand with water, but I'm going to do it both ways. This is a very silly diagram, but it's an attempt to explain electricity using water. Okay? And the idea is, it's kind of silly. We have a man here with a pump, like at a well. He's pumping water like at a well. You know, you've seen that. Have you guys seen water pumps like at a well? And so the man is pumping the water out of the pump here. It's flowing through the pipe around in a loop, in a circle, isn't it? And so in an electric circuit, we don't have a man and a pump, do we? But we have the battery voltage. And that pushes the electrons out. And then in an electric circuit, the electrons would be flowing like this. And then an electric circuit, instead of a pipe here, this would be a wire. And what we call resistance, it's either would be a big fat wire like we show here, or it would be a little skinny narrow wire. Again, I'm going to show you with water in just a second. This is a circuit diagram. It's very, very useful to be able to wire to a circuit diagram, which you guys are going to do today. So you notice we have these symbols. We have a battery, a switch, a light bulb. And we have our electrons, which are flowing through the light bulb, through the switch, and come back and being soaked up by the battery. And you're all going to do this in just a second. So what I'd like to do is have you all come up front, please. We're going to do some pretending. Some of you may remember this from grade 4, I don't know, but I covered this in grade 4. So we're going to pretend that these are electrons, just colored water. We're going to pretend, though, that these are electrons. We're going to pretend that this is a battery. Now it's just an ocean spray container, isn't it? And in a real circuit with a real battery, the electrons will come out one side, they flow through stuff, come back and get soaked up. Here, the water's just going to squirt out the hole here, and it's just a little silly. But the idea of the current flow and the voltage and all that is absolutely correct. and it's a good way to think about it and learn it is to use water, okay? So we're going to put electrons in our battery, and we're going to start out with a very weak battery, a low voltage battery that does not have very many extra electrons in it. And you notice you get a very wimpy electron current flow. So you see, there's low voltage, very little voltage, so it can't push the current out. So this would mean you'd have a very dim light bulb. Your motor would turn slowly. Your buzzer would not be loud. It would not annoy the teacher. Okay? You have very little energy if the voltage is low. It's wimpy. Okay? Now, if we put more electrons in the battery, so we get a much higher voltage. So this would be a nice, fresh, new battery, or maybe 2 or 3 batteries connected together in series, which you're going to be doing very soon. Now we'd have a battery with lots of voltage in it, and notice the difference in the current flow. We have a very powerful current flow. And I know it's silly, but the idea is now you'd have a light bulb that's very bright. Now you'd have a motor that turns fast. Now you have a buzzer that's very loud, okay? And so you just more energy in the circuit when you have more voltage in it. And it just pushes the current, the electron current, okay? Can you guys see that? I think this is, as silly as this is, I think it's a lot easier to understand this than it is trying to look at something on a slide. So I try to do it both ways. So we're going to try to save our electrons now. Come back. It's all nice and messy. Back. Now the second part of this is simply to help explain resistance. So I have another demonstration here, and I want you to notice what I have here. We're going to pretend these are batteries, and we're going to pretend that these are wires. And the idea is, you see this pipe, it's a big pipe here? That's going to work just like a big wire. So you see how this big wire has a lot of metal in it? Here's a wire with a lot of metal. Okay? Lots of room for the electrons to flow. Lots of metal in this one. And this pipe here is going to work just like that. And then next to it, there's a small pipe, a thin pipe, and that's going to work like a little wire. All right? So we're going to see what effect, this is what we call resistance, and this is going to show what effect this has. So first, we're going to run the electrons through a big wire. Okay? Now what happens when we do that? What happens when we run electrons through a big wire? Yeah, it makes the funny toilet noise, doesn't it? But yeah, you see how it just goes right through?
Do it once more.
Yeah. There's a lot of room here, you see? It's just like the wire itself. There's a lot of metal. There's a lot of room inside, so the electrons, it doesn't resist the electrons. So the electrons just go right through it, no problem. Okay, with a big wire. Lots of room inside, no problem. Now, watch the difference, though. When we run electrons through a little wire that has resistance. Now, see what happens? They have to back up. You have to wait their turn to get through. It's like lining up before you leave class and you have to wait for the kids in front of you, that kind of thing. So, when you have a small wire with resistance, less electrons get through because only so many can fit in. There's only so much room in a little tiny wire because it has resistance. So you see how that, it resists, it reduces, it cuts down on the amount of current that's flowing. You just have less current in the circuit. Very important. I'm going to show you why. So very carefully, I want you all to grab a light bulb and look at it. Let me pass these out quickly. Once you pass those out quickly, try to grab one quickly if you can, as carefully as possible because they're glass. So I want you to look inside the light bulb, see what you see inside of it. I like that. I like that. Okay.
Oh yeah, I see wires.
Yeah, yeah. Okay. So everybody got one? Okay. So who said that? What do we have inside? Who can tell me? Wires? What kind of wires? How would you describe the wires? Small wires?
Metal wires.
Metal wires. Now what are these?
Mine are spiral.
Yeah, spiral. Yeah, and they are spirally. That's so you can fit more in. Now, what do these wires have that we just talked about? What is it that they have?
Energy.
No. Oh, man. What a man. What a man. They have resistance. All right. The man gets a prize. Good for you. Okay. Slinky. Okay. So these little tiny wires, they're tiny, aren't they? They have resistance. The idea is now that when electron current flows through these tiny wires, they actually get very hot because the electrons are all squished together in that tiny wire, and the wire gets so hot it produces waves of light, which was a really big deal, a really important invention. So when Thomas Edison invented these, like more than 100 years ago, the electric light bulb, it was a very big deal. And the joke is I have a sign here, and I actually got this from the internet, but on the original electric light switches that Edison had, for on-off switches for lights, he actually had a sign saying basically, hey guys, don't try to turn on the electric light using a match, because people had never had light before without a flame, without fire. So people were walking into rooms, lighting a match and melting the on-off switch because they'd never heard of a light before that you didn't have to light with a match. You know what I mean? Like a candle or like a gas thing or something like that. So it was quite a big invention, the electric light bulb, okay? Now, I'd like could somebody collect those lights for me? Whoever would like to, please collect them. I don't want to, and while you're doing that, where's the little bucket? Oh yeah, put them back in there, carefully, please. So now I want to talk about switches. Let me talk about switches while we're doing that. Now, we have two kinds of switches you're going to use today. We have these knife switches. Watch me, please, everyone. We have these knife switches, and you connect them with these two screws here, okay? And then we have a regular wall switch that you'd have in a house, and they're connected with these two on the side. Thank you very much. These two screws here, okay? Now, how a switch works is this. The electrons come out from the battery with a wire. They come up to the switch, but if the switch is like this, what's between these two sides? Well, basically nothing, just air, right, and plastic, right? So electricity can't flow through that, can it? No, right? So this would be off. But when we do this, it's like Dr. Frankenstein's laboratory where he has a big knife switch. I don't know if you've seen that. But this would be off, and now here this is on. So when we put the switch on, now the electrons can flow through the switch, come out, go through stuff, and come back and be soaked up, all right? So that would be on. That would be off on your switch, okay? One final thing before you start wiring. You've got batteries, and they're in these little holders here, and they're pretty neat because you can save a wire. These holders will connect together, and you can connect two together like this. So whenever you hook up batteries together, you want to have a positive on one battery to the negative on the other. So a plus on one to the minus on the other, so the two batteries work together. Opposites attract is how you remember that. Okay? Like magnets, opposites attract. So the idea, though, is when you have these two battery holders, you can just put them together like this, and now that saves your wire. Now you got these two. Now that'll make a more powerful battery. So I'd like everybody to go back. Please open your worksheets. Find circuit 2, and then I want you to put the parts down on top of your diagram in circuit 2 and start wiring your circuits. Right. Very good, very good. Very good. Oh, this is silly, isn't it? It's from a toaster. You see that now?
We're done.
I took it out of my toaster. I fixed my toaster a couple times, so I couldn't fix it anymore, so I saved this. So it's a timer. It's a switch, but I would just use the regular switch for now.
I thought we broke it or
So
something.
no. So just put that here. Put your light bulb here. And where's your switch? Where's your... Do you have the other? Okay. You can use either kind. It doesn't matter. These are easier to understand. So you see that? Put that there. And then your light bulb. Where's your light bulb? Here it is. So now do your alligators. How are you guys doing?
We finished.
Okay, excellent. So once you finish 2, do 3. Once you finish circuit 2, do circuit 3. Remember to go plus on one to minus on the other. In all the world, there really are basically only 2 kinds of electric circuits. Even the most complicated circuits are really lots and lots of little ones stuck together. So the 2 circuits are series and parallel. I want to talk about the series first. Now you've heard, you know, like a TV series. Please stop wiring for a second and watch me, please, everybody. You know how there's like a TV series? Or there's the World Series, right? With baseball. So the idea, let's say you have a baseball game and a World Series. And then the next night you have another game. And then the next night you have another game. Then you have another game. It's a series. It's one thing after the other after the other. So it's a series, right? And it's the same way with these circuits. So in a series circuit, you have a number of different things, but the electrons have to flow from one thing to the other thing to the other. So see, with circuit 4, the electrons have to flow through the switch, through the first light bulb, to the second light bulb, back before they're soaked up. So all the electrons have to flow through everything in the circuit. Now, very important with the series circuit. Let's say one of these light bulbs burns out, or it's disconnected. Now we have a hole in the circuit. What's going to happen to the other light bulb in the series circuit if one of these light bulbs burns out or is disconnected? Who knows?
It's going to stop.
It's going to stop. All right, give the man a prize. Good job. So in a series circuit, it doesn't mean it's a bad circuit. It's just that's what it is. It's a series circuit. So if there's a hole or anything breaks in the series circuit, everything goes off. It's kind of like the old-fashioned Christmas tree bulbs. The old-fashioned Christmas tree bulbs were a series circuit. Okay. Now the second kind of circuit here is different. I want you to see why. This is what we call a parallel circuit. Now this is different. And the idea is the electrons come out of the battery, but when they get here, they have a choice. Some of the electrons can go through the first light bulb, come back and be soaked up. At the same time, other electrons can come and go through the second light bulb and come back and be soaked up. So there's a choice. There's two different paths, two different roads, two different ways that the electrons can go. So they can either go through this one, or at the same time others can go through that one. Now what's going to happen if one of these light bulbs here burns out or is disconnected? What's going to happen to the other light bulb? Who knows?
It's going to stay on.
It's going to stay on. And he deserves a prize too. You get a virtual prize, sir. Okay, so you see why this stays on? Because this connection is still good, isn't it? So parallel circuits are used for things like a building or a house or something like that. Because if one light bulb burns out, we don't want all of them going out. Series circuits are used for some things, parallel circuits are used for others. Now last slide, which I'm going to do very quickly. This is the most common circuit in the world, and it's both series and parallel parts of it. So the two batteries and the switch, see, they're all series. This is a series connection. All the electrons have to go through this part here. But this part is a parallel. That part's parallel, that part's series. So please continue wiring. And when you get through on number 6, tell me, I'll bring you a little toy to play with. That's just, instead of having a second wire, they just connect it inside to the metal. See, they just save a wire. It's a great idea. They do that a lot in cars. Cuts down the wires.
Can we have another one?
Okay. Oh, another one? What, it's not working? Oh. Oh, here, you can. Are you wiring, are you together with her? It's okay, go ahead. You need 2 batteries. Put the red to plus, 2 batteries in series, all right? Who else has done all 6? Oh, sorry. Okay, 2 batteries in series. The red goes to plus. The minus goes to the metal. Red goes to plus. 2 batteries in series, okay?
Give me a second. I just have to see what this is.
It's a test to see if you really like noise. We also have this fan toy you can play with, and motors too. There are motors in here, little motors you guys can use too. You can hook these up in the back, hook those little motors up. Right.
Hold on. Is this it?
You guys, good. So, 2 batteries in series. The red goes to plus, minus is the metal. Okay, 2 batteries in series. All right, good job, good job. All right, 2 batteries in series. The red goes to plus, the minus goes to the metal. 2 batteries in series, red goes to plus. What we have here is 4 of the large batteries. Each one of these has 4 batteries inside, so 16 batteries. It's still only 24 volts, so it's safe. You're not going to get a shock, but we are going to have sparks here. So we're using a special computer part called a capacitor. It's kind of like a welder. And what we're going to be able to do is make nice, juicy sparks. So I'll show you what to do. You're going to take the capacitor, and you're going to slide this screwdriver sideways until you touch the other piece of metal. So the 2 are together. The only thing to be careful of is I want to make sure everybody has their eye protection on, all right? Very slowly. It's going to make a big spark, okay? So, okay, so carefully slide it. All right, good job. And it looks very scary and dangerous, but it really is not. It really is not. Okay? All right, who's next? Did you see what to do? Yeah, between the 2. Don't be afraid of it, just be careful. Okay, good. Oh, look what happened. Look, it welded. She welded it. Look, she welded it. That's how it welded. She welded it. Good job.
Okay.
All right. Next. That looks clean. Yeah, and you're going to slide between the 2, making a nice juicy spark. All right, excellent. Good job. Look at that.
Whoa.
All right. Face. Whoa! It's not. You understand? It's not a shock. It's not a shock thing, but we don't want to spark somebody's face. Just between the 2 pieces of metal, you're going to go like this. Okay? All right. Excellent. Excellent. See how juicy that was? That was really good.
That was big.
Just slide. Pretend this is the screwdriver. You're going to go like that. Okay? Very carefully. Just don't get it in your face. That's why we have you wear the glasses. All right, good job. Excellent. Okay. I guess we have to go, unfortunately. You guys are a great class. Thank you.